I'd like to thank the organizers for having me here today. I'm going to be talking about Carleson's theorem and Schnorr randomness. So let me begin with some basics. So Carleson's theorem involves Fourier series, so of course I'm obliged to put up the standard picture that one gets in any undergraduate differential equations course demonstrating Fourier series, straight from Wolfram alpha. This is not the environment I'm going to be working in today, but it's enough to give a good idea if this is what you would like to visualize. In fact, I'm going to be working in the complex version of LP on the intervals negative pi to pi, which is just the space of all measurable functions from this interval to the complex numbers, such that this integral here is finite. So what has been known historically about the convergence of Fourier series? Well, Fourier himself asked, does the Fourier series of a continuous function actually converge pointwise to that function? And then it took a while. Dirichlet proved that if f were continuously differentiable, then you could know that its Fourier series converged to f. And then Dubois-Reymond proved in 1876 that life doesn't work quite as well as you'd like, that there is a continuous function whose Fourier series actually diverges at a point. And then, 30, 40 years later, Lucen conjectured that if f were an L2 function, then its Fourier series would converge to f almost everywhere. And it wasn't for another 50, 55 years that Lucen was proved right. In 1966, Carleson proved precisely Lucen's conjecture, and then another 2 years later, Hunt generalized it to any p greater than 1, still finite. So let me go ahead and give some basic definitions. So we'll just start with the standard definitions of a Fourier coefficient for any integer n and any f in L1 on that interval. Then Cn of f is 1 over 2 pi times the integral from negative pi to pi of f of t times e to the int dt. So Fourier coefficient, the nth one. And then for f in L1 from negative pi to pi and any capital N, a non-negative integer, S sub capital N of f is the sum from negative capital N to n of the nth Fourier coefficient times e to the int, and Sn of f is the n plus first partial sum of f's Fourier series. And we'll say that f is analytic if Cnf is actually 0 as long as n is negative. And then the other definition we'll need is that of a trigonometric polynomial. That's simply a function in the linear span of EINT for any n in the integers. And the degree of such a polynomial is going to be the smallest d in n, such that the d plus first partial sum of p's Fourier series is actually just equal to the polynomial. All right, so let me say very quickly what I'm going to prove today. We'll take p greater than 1 to be a computable real, and the first theorem is that if t naught in this closed interval is actually a Schnorr random point and f is a computable vector in LP, then the Fourier series for f does actually converge at t0. And then we have something almost like a converse to it, that if t naught is not Schnorr random, then there's a computable function whose Fourier series actually diverges at t0. So I should note very quickly that theorem 2 actually is stronger than theorem 1's converse, because it's possible to have an incomputable function that is nevertheless computable if you look at it as a vector. So I'll go on and I'll define functions versus vectors. Let me start, though, by describing a few more basic concepts in computable analysis. So we say that a point in the complex plane is going to be computable if there's some algorithm such that it will compute a rational point that is however close to the original point you like. More formally, it computes a rational point q such that the distance between q and z is bounded by 2 to the negative k for any k you want. And then the next thing we'll need is a trigonometric polynomial. We'll want to talk about a rational trigonometric polynomial, and such a polynomial is rational if each of its coefficients is a rational point. All right, and from here we can move into some more complicated things in computable analysis. These are ways to describe whether a function is computable, and if so, in what sense. So let's take p to be greater than or equal to 1. Let's take f to be an LP function on our closed interval. We'll say that f is a computable vector of LP if we can find some algorithm that computes a rational polynomial tau such that f minus tau is as small as we want it to be. So it can be approximated arbitrarily well by some rational polynomial, and there's an algorithm that can find that polynomial for you. Now, f from the complex numbers to the complex numbers, which is, I suppose, a more general definition than I mentioned I was going to give above, is going to be computable as a function if there's an algorithm p such that, well, let's see, whenever p is given an open rational rectangle as input, either it won't give an output or it returns an open rational rectangle in return. The next thing is that when it does halt on an open rational rectangle, then the open rational rectangle it outputs has to contain f of z for any z in the original rectangle that's even in the domain of f. And then finally, for any neighborhood of some z in the domain of f, and any neighborhood of f of z, there has to be an open rational rectangle that contains z in the original neighborhood, such that our algorithm p maps that open rational rectangle to an open rational rectangle within the neighborhood that we originally had for f of z. All right, so let me just give a few facts about these. So let's start with a nice proposition. Take a computable real number, take your f, just assume from here on out that those are the conditions on any result I give. So if f is a computable vector, then the p-norm of f and the sequence of Fourier coefficients for f are going to be computable. And if p equals 2, then that's reversible. And I admit I'm not going to use this corollary for anything, but I like it. That there is an incomputable vector f in L2 with a computable sequence of Fourier coefficients. And how do you do that? Well, you can find a computable sequence of positive rational numbers where the sum of their squares is actually incomputable. And, well, you just set f to be the polynomial, well, infinite polynomial, with that sequence as its coefficients. And then, of course, you get the right norm. F is going to be an incomputable function, but you started with a computable sequence of positive rational numbers. I just like that. So what's the point of giving a talk if you can't shove stuff like that in? Okay, so now I'm going to start working through the proofs of these results. It's going to be often more of an outline because the proofs involve a fair bit of just straight up complex analysis. And since this is a conference on what? Computability, randomness, and applications. It didn't seem quite right to do complex analysis at you. But let me show you how the proofs go. Okay. So what's the first theorem? Take your favorite computable real, take some Schnorr random point in that closed interval, take a computable vector in LP, then we're going to show that the Fourier series for f actually converges at that point. And the tool we're going to use this is a notion of a modulus of almost everywhere convergence. Now, in computability, we have a modulus of convergence. Yes, the point at which, or the stage at which, the approximation to a function actually gives you the function up to a certain point. Well, here what we have, we start with a sequence of functions on our favorite interval, and we say that we have eta as a modulus of almost everywhere convergence if for every k and m, well, what is that definition saying? It says essentially the sequence of functions converges, and we have, I did not check, do we have a, yes we do. We have the set of points in our interval. We're going to say that there are some m and n greater than that modulus, where the difference between fn of t and fm of t is large for some given value of large. And we want the set of points where the difference between fn and fm for some n and m sufficiently far out in the sequence, we want there not to be very many of those. So we're basically saying that that eta km takes you out far enough in the sequence that there aren't very many points where you can even find two terms of the function sequence after that where the values differ by very much. Okay.
But the existence of such a thing doesn't guarantee almost everywhere convergence.
Sorry, yeah?
So imagine such a thing exists.
Mm-hmm.
It seems that this doesn't imply almost everywhere convergence. Because if you have just needle things which go smaller and smaller, the modulus exists while that's not a...
Okay. Okay, let's keep going. Maybe we'll answer your question. Okay, so now let me put together the two lemmas that we're going to use to prove this theorem. The first lemma is, suppose you have your computable real P, suppose you have a computable vector in LP, then the partial Fourier series will have a computable modulus of almost everywhere convergence. Then we can say, suppose that we have a sequence of functions for which there is a computable modulus of almost everywhere convergence, then that sequence will converge at every Schnorr random real. Put these together, you get the theorem that we're hoping for. Okay. So let's start by looking. Sorry, yeah? Yeah. The original theorem. Have we feasted our eyes sufficiently long yet? Can I move on? Okay.
But what is uniformly computable? There is no requirement of being uniformly continuous, just which it means that every function can be computed given the number.
Uniformly computable must imply
The continuity, yeah?
uniform.
Yeah.
No, then what is uniformly computable? Say it again. So
You mean for the first
I thought
time?
that for every n there is an algorithm which computes fn. Do you require something else?
Well, that would have to be effective.
Effective,
Yeah.
The procedure taking the end to the algorithm must be computable. That's what you mean.
Yeah, but then I don't understand. So imagine we have fn, which are just needles.
Okay.
And these are small needles, and they move along the interval,
Okay.
all the interval, and then they become even smaller.
No, it doesn't have these modules of almost cellular continuity. If you think it, because there is a, if you look at the definition.
Okay, then maybe can you show again?
Perhaps.
Previous
Yeah.
slide.
Oh, yeah, it's, sorry, it's not for,
Yeah.
not a measure of
Right.
union is small. Okay,
Right,
sorry.
right. Okay. So let's look at the first lemma. We're going to show that if we have a sufficiently nice vector, then the partial Fourier series have such a modulus. So how do we build this? Okay, so let's build our eta, let's fix k, let's fix m. Well, f is a computable vector. That means we can approximate it arbitrarily well by some trigonometric polynomial. So let's build this rational trigonometric polynomial. Well, we can make the difference between them as small as we like. And we're going to choose that degree, that difference, to be 2 to the negative m plus k plus 3 times C inverse. What is C inverse? It comes out of an theorem from analysis called Pfefferman's inequality, which essentially says that under these conditions, such a C will exist. There we go. And then we just say, well, now we have a perfectly good modulus. Eta km is just going to be the degree of that polynomial. So then we have to show that this is, in fact, the sort of modulus we want. Let's say that for any g, let's define this thing. In our paper, we very meaningfully call it E hat sub kg. It's just the set of points in our interval where the sup of the partial Fourier series, the n plus first one, for g, is going to be at least 2 to the negative k. And you might have noticed by now that this eta stops showing up, which is bad notation, but I assure you that to make the eta show up, I would have had to define many more things that probably you do not want to see explicitly. So let's just say that when we take g to be the function we want it to be, the difference between f and the rational trigonometric polynomial tau, when we're choosing our k, the eta shows up in our choice of k. So think of this k as being a function of our eta, and everything is okay. Okay, that is what I am hiding under lots of manipulations. Okay, so yes, we're going to use it. So Pfefferman's inequality says that there is a constant that makes this true. And then that allows us to look at this sup here for the function we're actually interested in. Pfefferman's inequality says that this thing is less than or equal to c times p norm of f. And since we said that this norm has to be less than or equal to c inverse times 2 to the negative m plus k plus 3, well, let's just multiply. We now have a very nice bound. The c from Pfefferman's inequality just disappeared. It was an intermediate step. Okay. And then we can apply Chebyshev's inequality to, and again, I'm not going to particularly worry about what E hat is here, but essentially this is going to be the measure of the set that we are interested in when we talk about a modulus of almost everywhere convergence. And then we can use Chebyshev's inequality to say, well, this thing is less than pull this here, choose k plus 2. Chebyshev's inequality lets you do that. Then we collapse it down to 2 to the negative m. So essentially the e hat k plus 2 of that difference of functions is, it turns out to be this set. So we've now bounded the size of that set as desired. Okay, so now we know that such a function f will give us such a modulus of almost everywhere convergence. Now we have to show that having such a modulus is going to give us convergence. So let's see. Second lemma. Again, suppose we have such a sequence, we have such a modulus, then the sequence will converge at every Schnorr random real. Well, here we're going to use a more recent characterization of Schnorr randomness. We have a Schnorr integral test from Miyabe. So what is a Schnorr integral test? It's a lower semi-computable function such that when you integrate it, you get a computable real over the space, and a point is going to be Schnorr random if and only if, when you plug it into that T, you get something finite for every Schnorr integral test you like. So let's define a Schnorr integral test. Let's choose eta to be our computable modulus of almost everywhere convergence. And let's just abbreviate eta kk, so we're saying we want to be off by at least 2 to the negative k, no more than 2 to the negative k of the time. Let's just call eta kk nk. And now, for every k and n, every t in our interval, we're going to define gkt. Well, what is that? At the most, it's 1. At the least, it's going to be the maximum difference you get for fm minus fnt for m and n between nk and nk plus 1. So eta kk to eta k plus 1, k plus 1. And now you see why I bothered to introduce n sub k. It's because if you left it as eta kk, eta k plus 1, k plus 1, it wouldn't have fit on the slide. Seemed like a good choice. Okay. So essentially gkt is keeping track of how far apart you're allowed to be at t for approximations to f within a particular range in terms of the sequence of the moduli of almost everywhere convergence. Well, okay, this is going to be computable. F is nicely computable, or a computable vector. G should be computable. So let's just take our Schnorr integral test to be the sum of the GKs. And how do we show it's a Schnorr integral test? Well, at least it's going to be lower semi-computable from the construction. Showing it's computable involves lots of manipulation, and I have, let's say, 45 minutes at the most. So let's just leave it as lots of manipulation. So now we've got our Schnorr integral test. Let's show that whenever fn t0 diverges, then the Schnorr integral test actually is infinity. Gives you infinity here. So, okay, let's suppose it diverges. Then there's going to be some k0 such that the lim sup over m and n of that difference, fmt0 minus fnt0, that's at least as big as your 2 to the negative k0. So what we'd like to do is we would like to show that for all k1, then the sum of gk t0 past that, the sum past that k1 is going to be at least 2 to the negative k0. Well, we chose our k0 carefully. We can find an m and an n such that as long as we are past n sub k1, we can find m and n where that sum is at least that, and then we want to show that this sum, which is our t, is at least as big as this, yes? So essentially all we do is we form a telescoping sum, we apply the triangle inequality, we end up with this, and then that gives us that our Schnorr integral test here is at least as big as the thing we want. Life is good. So here's our first result. So flipping back, now we know that if you have a Schnorr random point, then you've got a sufficiently nice function, then the Fourier series for the function will converge. Now, let's look at the converse. So, what are we saying here? We have a point that's not Schnorr random. So there's a computable function f whose Fourier series diverges there, and now when we talk about a function, we're talking about a computable function, not a computable vector. And this proof follows a construction of, I'm going to say Kahane. Anyone who knows the pronunciation better, I would love a correction at this point. Kahan, thank you. His location was nationality entirely unclear from the articles. Good, yes. Which would have been my guess because I did actually have to translate both articles we had to read for this. Okay. So, let's see. I am going to speed very quickly through all of the necessary lemmas for this. Feel free at this point to stop reading especially carefully. Essentially, it's a sequence of lemmas that are heavier on the not even computable analysis. They are lemmas from analysis. I am not going to prove them. Let me just say that all of the constructions in these lemmas are uniform. The other thing to note is that all of them build on each other. So you'll note that they all, so far, start out with the same hypotheses, and they all just build. So really the one you would need to look at is this, the last one. Suppose the standard supposition for these. The main thing that I'm going to ask you to remember here is that we have a bound on n for Sn of our computable trigonometric polynomial p at t. That sup is at least negative 1 over 4 pi natural log of lambda g2 pi for all t in our computably compact subsets and such that p is, again, sufficiently nicely behaved.
So what is lambda?
Ah.
And lost. Probably you said this already.
No, I didn't. It's okay. Memory's fine. Oh dear.
Lambda of g.
Lambda of g, yeah. Oh, shoot. Can we save that for the Q&A, whereupon I will go to the paper and take a look? Yeah. I actually think the only measure we use in this paper is Lebesgue measure. So I think it is Lebesgue measure, and I think we simply accidentally used 2 different symbols to mean Lebesgue measure. Yeah. I think we used mu, and Kahan, I believed, used lambda, so we kept his notation when we were working from the lemmas, yeah. I was thinking, wait, I always use mu for that, it can't possibly be Lebesgue measure. Kahan uses lambda. Okay, so the proofs are all analytic and uniform. Now, given these lemmas, so we all remember the negative 1 over 4 pi bit. That's going to pop up, nothing else about them will. So let's suppose that we have a point that's not Schnorr random. Then you're going to have a Schnorr test where t is contained in its intersection. So now let's use that. We're going to build an array of closed rational intervals. where the 2nth component of that Schnorr test is the union of the intervals in row n, and those intervals are going to be not necessarily pairwise disjoint, but they will be overlapping at a null level. The measure of their intersections will be null. Okay, so now for every n, we're going to be able to compute a sequence, mn0, mn1, so on and so forth, such that the measure of the 2 to the nth component of the Schnorr test and the union up to that point, mnk, of all of those intervals, the measure of that difference is going to be very small. It's a Schnorr test. This is something we're allowed to do because we actually do know the measure of this. Okay, so after we've got that, let's define this sequence. I had to fiddle a little bit with gn0. I'm going to say that that's the union of the, those intervals intersected with the interval we care about for all j less than or equal to mn1, and then gnk is going to be the union of all of those intervals intersected with the interval we care about for essentially the points, those intervals that are indexed between mnk and mnk plus 1, which means that we can bound the measure of each of those g's very usefully, right? So now, here's where the third lemma comes in. If we've got n and we've got k, then we can use that third lemma. Remember, it looked remarkably like this, except there was just a g there before. We can get a trigonometric polynomial, sufficiently nice, where the sup of this absolute value of the n plus first partial sum of that polynomial's Fourier series at t, that sup has, over all n, has to be at least this big for every t in that gnk. Remember that the gnk is essentially part of the 2 to the nth component of the Schnorr test, and one whose measure we can reasonably talk about. So now we're going to define a new polynomial where it's just going to be a certain scaling of the original polynomial that we got out of lemma 3. And then that scaling allows us, because we know the measure of each of the g and k's. We've now scaled that polynomial. We now have a much more attractive bound for the sup of the partial sums of this new polynomial. It's at least 1 over 8 pi. Okay. And the next thing we want to do, and I will simply quietly tell you that I'm doing it. We're going to compute an array that produces, think of it as nice Fourier coefficients. We're going to use those Fourier coefficients to define a function f, whereas remember we're assuming that t0 is not Schnorr random. We want to find a function, a computable function that does not converge at that point. We're working on building that function. So think of it as f is the sum of those scaled polynomials, the p and k's. We have nice Fourier coefficients to go with each of the p and k's. And because we did scale those, because we're not using just p, we can bound the norm of p and k. That's enough to make f a computable function. Okay. So now we have to show that F's Fourier series actually diverges at the point we want it to diverge at. So how are we going to do this? Well, we're going to try to show that the sup over kappa m and kappa n of the partial Fourier series of F at the point t0 at the m plus first and the n plus first is big enough. It's at least 1 over 8 pi. So how are we going to do this? We're going to fix an n0, and we're going to choose an n such that the pair n comma 0 is at least that big, and we're going to choose k such that t naught is in g and k. Why can we do this? We know t is in every component of the Schnorr test. It's certainly in the 2 to the nth component of the Schnorr test. Therefore, it's in one of the g and k's. Let's choose that one. Okay. So this is the part where I feel slightly guilty about not building the RNKs in front of you. If you read the paper, you would not feel that I had made the wrong decision here, I think. But I'll just say that we chose the RNKs very carefully. We chose this array so you can find m and, because we need more notation, n prime, such that think of it as the n comma kth function we're looking at. That function is actually the difference between the n plus first term in the Fourier series for f and the m plus 1 term in the Fourier series for f. Okay. And we can also be sure that m is at least as big as nk, which is at least as big as n0 under any sensible pairing function you like. And by our particular choice of p and k, we can find an n, cap n, between our m and between our n prime, such that that sup actually is big enough. Okay. So we have our divergence. This is what we were hoping for. Okay. So again, if you would like to talk later in detail about what exactly the array was that I built that made this sort of magical situation happen, I'll be happy to talk about that offline. But now maybe you can get a little bit of an idea of how that array was in fact constructed. We wanted to make sure that we could find a point for whichever n and k turned out to be necessary. We could find a term that would make this sufficiently true. That would mean that our array of now not just coefficients, but of functions, of rational trigonometric polynomials, gave us the differences we were looking for. Okay, so I think this is the first time anyone has characterized randomness in terms of a Fourier series. You know, we've been looking at ergodic theory, differentiability, many other things, but we were quite excited to be able to look at it in terms of Fourier series as well. So the paper's on the archive, if you're interested. Hopefully we'll be able to change that from submitted to accepted at some point soon. But thank you for your attention.